to the geometrical shadow region. This is the obstacle in the path of light, basically because of diffraction of light. So, Fraunhofer diffraction converging beam is used. Is the ability of that instrument. What the instrument has to do, it has to produce is the wavelength of light used, whatever color light has been used. Hello students, this is SD Sir from the Temple of Excellence, Vidhyaashram Pre-University, Mysuru. The previous session, we have completed our discussion on the phenomenon of interference, where we derived an expression for fringe width of interference pattern, and also we mentioned the conditions for sustained interference. In my today's class, we will learn one another beautiful phenomenon, something called diffraction of light. Again, a phenomenon which is associated with the wave nature of light. Phenomenon which actually explains the formation of shadows. So, in my today's session, we will discuss about the phenomenon of diffraction of light. Now, the phenomenon of diffraction was first discovered by the scientist Grimaldi. So, Grimaldi was the scientist who first explained the phenomenon of diffraction. Now, what is this diffraction of light? It is the phenomenon of bending of light waves. The key word that has to be used to define diffraction is bending of light. This is very much different from scattering of light. Diffraction has nothing to do with scattering. It is bending of light, where around the edges of obstacles, if there is an obstacle, a barrier in the path of a light wave, I place some obstacle, some barrier in the path of the light. At the edge of this obstacle, light bends. At the edge of that barrier, light bends and then spreads into the geometrical shadow region. After light is bent, it is spreading itself to the geometrical shadow region. And that is what we call diffraction of light. So, the very word diffraction can be explained using two terms. The first term is bending of light and spreading into the geometrical shadow region. This is what we call diffraction of light. If you have clearly observed, when light passes through a keyhole, circular shaped or circular pattern shadow is formed. That is basically because of diffraction of light. So, how do we define diffraction of light? It is the phenomenon of bending of light waves. Light waves bend where? At the edges of the obstacles. Some obstacle or some barrier in the path of light and spreads into the geometrical shadow region. And this is defined as diffraction of light. Now, there are two types of diffraction. One is called Fresnel's diffraction and the other one is called Fraunhofer diffraction. So the two types of diffraction possible is, the first type is called Fresnel's diffraction and the second type is called Fraunhofer diffraction. So these are the diagrams which will depict Fresnel and Fraunhofer diffraction. So this is Fresnel and this is Fraunhofer. Now, let us study the differences between Fresnel's diffraction and Fraunhofer diffraction. Fresnel's diffraction says the source and the screen. Source andre, something which is emitting light waves. It is the source of light waves. So this is the source. And this is the screen on which diffraction pattern, here we call diffraction bands, is obtained. So, source of light, screen on which diffraction pattern is obtained. In Fresnel's diffraction, source and screen are at finite distance from the obstacle. You can measure the distance between the source and the obstacle and the obstacle and the screen. The source and the screen, they are at finite measurable distance from the obstacle or the barrier. This is the obstacle in the path of light. At the edges, light bends. Whereas in Fraunhofer diffraction, the source and the screen are at infinite distance from the obstacle. Non-measurable distance from the obstacle. So, Fresnel, source and screen are at finite distance from the obstacle. Fraunhofer, source and screen are infinite distance from the obstacle. Again, Fresnel, spherical or cylindrical wavefront is used, whereas Fraunhofer, plane wavefront is used. So this is always asked as 1 mark. For Fresnel's diffraction, the nature of the wavefront used is either spherical or cylindrical. Fraunhofer, it is a plane wavefront. Fresnel, if you observe, we don't have any convex lens. So Fresnel's diffraction does not involve the usage of convex lens. We don't use convex lens to get diffraction pattern from Fresnel's diffraction. Whereas Fraunhofer, 2 convex lenses are used. Converging lens. So no convex lens in the case of Fresnel's diffraction, 2 convex lens in the case of Fraunhofer diffraction. Fresnel's diffraction, diverging beam is used. Fraunhofer diffraction, converging beam is used. And finally, Fresnel's diffraction, mathematical treatment, mathematical analysis, mathematical understanding is a bit complex. Whereas Fraunhofer, mathematical analysis is simple. So these are the differences between Fresnel and Fraunhofer diffraction. Source and screen, finite distance from the obstacle. Source and screen, infinite distance in the case of Fraunhofer. Spherical or cylindrical wavefront here. Plane wavefront in the case of Fraunhofer. No convex lens. 2 convex lenses are used. Diverging beam of light, converging beam of light. Mathematical analysis is simple. Mathematical analysis difficult in case of Fresnel. This is the intensity distribution curve in case of Fraunhofer diffraction. Central band is the intense band, which is called central maxima, brightest band. This is called secondary minima, dark bands. Secondary maxima, bright bands, but less intense when compared to the central maxima. Now, this is very, very important. You may be asked a numerical also based on this topic, something called resolving power of a microscope. We will be discussing resolving power of a telescope also. But now I refrain my discussion to something called resolving power of a microscope. Now, I place 2 dots or 2 points very close to each other. In this region, I have placed 2 points which are very, very close to each other. Are they clearly, distinctly separated? No. I cannot analyze them to be distinct and unique. They are very close to each other. So, what is the meaning of the word resolve? The word resolve means to break. In this context, in this criterion, the word resolve means to separate, break, or separate. So, resolving power of any optical instrument, is the ability of that instrument, capability of that instrument to produce clear, separate, distinct images exactly like this. The image has to be clear. The image has to be well separated, distinct of 2 closely lying point objects. If the 2 objects are very closely placed like this, very close to each other, the optical instrument has to resolve it clear, separate, and distinct. And that is what we call resolving power. So, resolving power of any optical instrument is the ability of that instrument. What the instrument has to do, it has to produce clear, separate, and distinct, well separated images of closely lying point objects. If the 2 point objects, small objects, are very close to each other, the optical instrument has to resolve it properly. It has to produce clear, distinct, and separate image of those 2 point objects. Now, what is a microscope? Most of the times, you have used it in your bio lab. You will be doing an experiment using traveling microscope. But this is optical microscope. It is an optical instrument. Naturally, microscope is an optical instrument used to magnify small objects which cannot be seen through our naked eyes. Very, very small objects, size in the magnitude of a virus or a bacteria, which you cannot see through your naked eyes, can be magnified using an optical instrument called microscope. So microscope is an optical instrument which magnifies very, very small objects which cannot be seen through our naked eyes. Now, important definition. This carries 1 mark in the exam. Limit of resolution. ಏನ್ ಹೇಳ್ದೆ ರಿಸಾಲ್ವಿಂಗ್ ಪವರ್ ಅಂದ್ರೆ the ability of an optical instrument to well separate, produce clear, distinct, separate image of closely lying point object. Now we place a limit on this resolving power and call limit of resolution. Limit of resolution for a microscope is the minimum distance. It is the minimum distance between two closely lying point objects. There are two closely lying point objects. Minimum distance between them where these two objects appear to be just resolved, just separated. That minimum distance is called limit of resolution. Please to know this term, limit. Limit of resolution. Minimum distance between two point objects whose image appears to be just resolved. That is called limit of resolution. And it is given by the expression D. Limit of resolution is lambda divided by n sin theta. Then pitkolli expression na limit of resolution D equals lambda divided by 2n sin theta, where lambda is the wavelength of light used, whatever color light has been used to magnify the object, wavelength. N, refractive index of the medium between the object and the objective. Generally, n represents refractive index. This is very important. Theta is called semi-vertical cone angle. If you observe here, this is theta, semi-vertical cone angle. And this n sin theta together is called numerical aperture. So lambda, wavelength of light used, n, refractive index, theta, semi-vertical cone angle, n sin theta, numerical aperture. If so, then resolving power is measured as the reciprocal of limit of resolution. Always remember, resolving power is measured as the reciprocal or the inverse of the limit of resolution. So resolving power of a microscope becomes the other way, 2n sin theta divided by lambda, reciprocal of limit of resolution. How do we increase the resolving power of a microscope? So if you observe, resolving power is directly proportional to n and theta. So we use oil of high refractive index to increase the resolving power of a microscope. Oil of high refractive index is used, which is called oil immersion microscope. And UV radiations of smaller wavelength called UV microscopes. So this is how we increase the resolving power of a microscope. 2 marks. Yes, they ask in the exam. Use oil of high refractive index. It is called oil immersion microscope. Use UV radiations of smaller wavelength. It is called UV microscopes. So students, in this session, we clearly understood what is diffraction, differences between Fresnel's and Fraunhofer diffraction, and resolving power of a microscope. Next, we understand resolving power of a telescope. Until then, have a fine day. Thank you.